In the present lecture, we will discuss the two-phase simplex method with example problem. Let's see the problem. Use two-phase simplex method to solve the following LP problem. Minimize z equal to x1 plus x2 subject to the constraint. First one is 2x1 plus x2 greater than or equal to the 4. Second one is x1 plus 7x2 greater than or equal to the 7. x1 comma x2 are greater than or equal to the 0. So let's see the solution. Here given LP problem is minimization model. So first step is convert the given LP problem objective function into maximization form by multiplying the -1. Then objective function will become the maximize z equal to minus x1 minus x2. Next, we have to convert the general linear programming problem into standard form of linear programming problem by introducing the surplus and artificial variables in the given constraint. So first constraint is 2x1 plus x2 greater than or equal to 4. So we have to introduce the surplus variable minus s1 and artificial variables a1 in the first constraint. Similarly, second constraint is x1 plus 7x2 greater than or equal to the 7. So we have to introduce the surplus variable minus s2 and artificial variable a2 in the second constraint. Then constraints will become 2x1 plus x2 minus s1 plus a1 equal to the 4. Second constraint will become the x1 plus 7x2 minus s2 plus a2 equal to the 7. And all the basic variables and surplus variables and artificial variables are the greater than or equal to the 0. That is x1, x2, s1, s2, a1, a2 are greater than or equal to the 0. Next, we have to find the initial basic feasible solution. For this, we have to assume the basic variables x1 and x2, surplus variables s1 and s2 are considered the 0 and substitute these values in the given constraints. Then we will get the a1 and a2 values. So these a1 and a2 values are the initial basic feasible solution. So let's substitute the x1 equal to 0, x2 equal to 0 and s1 equal to 0 in the first constraint. a1 value will become the 4. Similarly, substitute the x1, x2, s2 are considered the 0 and substitute in the second constraint. We will get the a2 value, that is the 7. So next we have to go for the two-phase method. So first we have to solve the first phase for the eliminate the artificial variables. So first we have to assign the cost value -1 to the each artificial variable and cost value is the 0 for the other variables. Then we have to modify the objective function. So that is maximum z equal to 0x1 plus 0x2 plus 0s1 plus 0s2 minus a1 and minus a2. So here we are assigning the cost values. So Cj values for all the variables except the artificial variables 0 and Cj value for the artificial variables -1. Then objective function will become the 0x1 plus 0x2 plus 0s1 plus 0s2 minus a1 minus a2. And constraints are the 2x1 plus x2 minus s1 plus a1 equal to the 4, x1 plus 7x2 minus a2 plus a2 equal to the 7. Next, to construct the initial simplex table. So this is the initial simplex table. So here CB is the cost coefficients for the initial basic variables, and b is the basic variables, xb is the initial basic feasible solution, and x1, x2, s1, s2, a1, a2 are the basic variables, surplus variables and the artificial variables. So first you have to fill this table. So initial basic variables are the a1 and a2 and its cost coefficients are the -1 and -1. And initial basic feasible solution is the, for a1 value is the 4 and a2 value is the 7. So next we have to CJ values. Cost coefficient values are the, we are assigning the 0 for all the variables and -1 for the artificial variables. So for the artificial variables, -1 and -1, remaining all the variables cost coefficients are the zeros. And here we have to fill the coefficients of the its values by observing the constraints. So by observing the first constraint, x1 coefficient is the 2 and x2 coefficient is the 1, s1 coefficient is the -1, there is no s2, so s2 coefficient is the 0 and a1 coefficient is the 1, and here there is no a2 in the first constraint and a2 coefficient is the 0. Similarly, by observing the second constraint equation, x2 coefficient is the, x1 coefficient is the 1, x2 coefficient is the 7, and here there is the no s1, so 0, s2 coefficient is the -1, and there is the no a1, its coefficient is 0, and a2 coefficient is the 1. Next to calculate the Zj minus Cj values and check the basic feasible solution for optimality. So Zj minus Cj is the summation of Cbj xj minus Cj. So first you have to calculate the Zj minus Cj for the first variable, that is the for x1. So Z1 minus C1. Z1 minus C1 will become the CB x1 minus C1. So it is the CB into the x1 coefficient. So -1 into 2 plus -1 into 1 minus Cj. For x1 Cj value is the 0. So it is the -3. So next we determine the Z2 minus C2 for the x2 coefficient, that is -1 into 1 plus -1 into 7 minus 0. So it is the -8. Next for the Z3 minus C3 for the third variable, that is the S1 variable, -1 into -1 plus -1 into 0 minus 0. So it is the 1. So next Z4 minus C4 for the S2 variable, it is the -1 into 0 plus -1 into -1 minus of 0, it is the 1. Next for the Z5 minus C5 for the A1 variable, it is the -1 into 1 plus -1 into 0 minus of -1, it is the 0. Next Z6 minus C6 for the A2 variable, its value is the -1 into 0 plus -1 into 1 minus of -1, its value also 0. So if all the Zj minus Cj values are the greater than or equal to the 0, then we get the optimal solution. If any Zj minus Cj values or any one Zj minus Cj value is the negative value, we are not getting the optimal solution. If the Zj minus Cj values are the negative for the more than 1, we have to select the most negative value. Here Zj minus Cj values are the -3, -8, 1, 1, 0, 0. and Z1 minus C1, Z2 minus C2, or we are getting the negative values. So we are not getting the optimal solution. Then among these two have to select the most negative value. So most negative value is the minus 8 for the x2 variable. So x2 column we are calling as the key column, and also it is calling as the incoming vector. So x2 variable enter the basis. So previously we are not considering the x2 as the basic variable. Now we have to replace x2 will come in the basis. So x2 variable enters the basis. So next step is calculate the minimum ratio of xb divided by coefficient of incoming variables. So that is the for the first row xb value is the 4 and incoming variable coefficient is the 1. So 4 by 1 equal to the 4. So next for the second row xb value is the 7 and incoming variable coefficient is the 7. So 7 by 7 is the 1. So here minimum ratio is the 1 and indicated by arrow, and A2 is the outgoing vector. So here artificial variable A2 leaves the basis. And next we have to identify the common element in the key row as well as the key column. So here key row is the A2 row and key column is the x2 column. So common element in the A2 row and x2 column is the 7. So 7 we are calling as the key element. So next we have to construct the new simplex table by entering the incoming variable x2. It is replacing in the outgoing variable A2. So now we have to construct the new simplex table by we have to replace the outgoing variable A2 with the incoming variable x2 in the basis. Now basic variables are the A1. Now here replacing the x2 and its cost coefficient are the for the A1 it is the -1 and for the x2 it is the 0. So next applying the following row operation to get an improved solution. First one is the R2 new equal to R2 volt divided by key element. Here key element is the 7. So here R1 volt and the R2 volt are the row 1 and row 2 in the old simplex table, and R1 new and R2 new are the row 1 and row 2 in the new simplex table. Now we have to modify the R2 new in the new simplex table second row by the R2 old elements. So second row old elements divided by key element. Here key element is the 7. So R2 old elements are the 7, 1, 7, 0, -1, 0, -1 and divided by 7 we will get the R2 new element. So 7 by 7 is the 1, 1 by 7, 1 by 7, next 7 by 7, 1, 0 by 7 it is the 0, -1 by 7, -1 by 7, 0 by 7, 0 and 1 by 7 is the 1 by 7. Next another row operation is the R1 new equal to R1 volt minus R2 new. So here R1 volt elements are the 4, 2, 1, -1, 0, 1, 0 and R2 new elements are the 1, 1 by 7, 1, 0, -1 by 7, 0 and 1 by 7. So now R1 volt minus R2 volt is the 4 minus 1, 3, 2 minus 1 by 7, 13 by 7, 1 minus 1, 0, minus 1, minus of 0, minus 1, 0 minus of 1 by 7, 1 by 7, 1 minus 0, 1, and 0 minus 1 by 7 is the minus 1 by 7. So here always you have to remember. So key element should be become the 1. So that's why here divided by, we are doing the operation is R2 whole divided by 7. Moreover, remaining element in the incoming vector. So remaining elements here having the only 1. Here we have to get the 0. For this one I have to use the with the help of the R2 new rule. So that's why we did these two operations. So this is the new simplex. Next step is once again I have to calculate the ZJ minus CJ and check the basic feasible solution for the optimality. So Z1 minus C1 so is the minus 1 into 13 by 7 plus 0 into 1 by 7 minus 0. It is the minus 13 by 7. Z2 minus C2 is the minus 1 into 0 plus 0 into 1 minus of 0. It is the 0. Next minus 1 into minus 1 plus 0 into 0 minus of 0. It is the 1. Next minus 1 into 1 by 7 plus 0 into minus 1 by 7 minus 0. It is the minus 1 by 7. And next one is the minus 1 into 1 plus 0 into 0 minus of minus 1. It is the 0. And next one is the minus 1 into minus 1 by 7 plus 0 into 1 by 7 minus of minus 1. It is the 8 by 7. So here ZJ minus CJ values are the minus 13 by 7, 0, 1, minus 1 by 7, 0, 8 by 7. If all the ZJ minus CJ values are positive, we get the optimal solution. But here Z1 minus C1 and the Z4 minus C4 are getting the negative values. So we are not getting the optimal values. Among these two values, we have to select the most negative value. That is the minus 13 by 7. So that is for the x1 column. So in this x1 column, we are calling as the key column and also we are calling as the incoming vector. So x1 variable is the incoming variable. So it will be entered into the basis. Next we have to calculate the minimum ratio of xb divided by coefficient of incoming variables. That is the 3 divided by 13 by 7, which means 3 into 7 by 13, that is the 21 by 13. And next 1 divided by 1 by 7, it is the 1 into 7, it is the 7. So among these two, so minimum ratio is the 21 by 13 for the A1 row. So minimum ratio is 21 by 13 and indicated by arrow, and A1 is the outgoing variable, outgoing vector, and A1 is the outgoing variable. So artificial variables A1 is leaves the basis. So next we have to identify the key element. So it is the common element in the key row as well as the key column, that is the 13 by 7. So next once again I have to construct the new simplex table by entering the incoming variable. So next to construct the new simplex table. So here I have to replace the A1 with the x1 and its coefficients are the 0 and 0 for the x1 as well as the x2. And next we are applying the following row operation to get the improved solution. First row operation is the R1 new equal to R1 volt divided by key element. So that is the R1 new will become the R1 volt divided by 13 by 7. We can be say that one the R1 volt into 7 by 13. So for the first element 3 into 7 by 13, that is the 21 by 13. So 3 by 17 into 7 by 13, it is the 1. 0 into 7 by 13, 0. Minus 1 into 7 by 13, minus 7 by 13. And 1 by 7 into 7 by 13. So it is the 1 by 13. And 1 into 7 by 13, 7 by 13. Minus 1 by 7 into 7 by 13, it is the minus 1 by 13. So next row operation is the R2 new equal to R1 volt minus of R1 new divided by 7. So first write down the R2 old elements. So that is the 1, 1 by 7, 1, 0, minus 1 by 7, 0, 1 by 7. So next write down the R1 new elements, that is 21 by 13, 1, 0, minus 1, minus 7 by 13, 1 by 13, 7 by 13, minus 1 by 13. So next write down the R1 new divided by 7. So here 21 by 13 into 1 by 7, 3 by 13, and 1 into 1 by 7, 1 by 7, 0 into 1 by 7, 0, minus 7 by 13 into 1 by 7, minus 1 by 13, 1 by 13 into 1 by 7, 1 by 91, 7 by 13 into 1 by 7, so 1 by 13, minus 1 by 13 into 1 by 7, it is the minus 1 by 91. So next we have to do the R2 volt minus R1 new divided by 7. That is the, so 1 minus 13 by, sorry, 3 by 13, it is the 10 by 13, 1 by 7 minus 1 by 7, 0, 1 minus 0, 0, 0 minus of 1 by 13, 1 by 13, minus 1 by 13, minus of 1 by 91. It is the minus 20 divided by 91. 0 minus of 1 by 13, it is the minus 1 by 13. 1 by 7 minus of minus 1 by 91, it is the 20 by 91. So next we have to calculate the ZJ minus CJ values. So ZJ minus CJ is the, so multiplication of CB value with the XJ coefficient minus of CJ values. So here observe the CB values are the 0. Then we will get the, so we have to write down the minus of CJ values. So here we will get the 0, 0, 0, 0, and minus of minus 1, it is the 1, and minus of minus 1, it is the 1. So here observe the, all the ZJ minus CJ values are the positive. Moreover, I have to check the Z star value, that is the multiplication of CB values with the XB. So that is also we are getting the 0. So maximum Z star also 0, and all ZJ minus CJ values also greater than or equal to the 0. So in the condition of ZJ minus CJ's, third case is satisfying. So that is the, so Z star is the 0, and there is the no artificial variables appears in the basis. Moreover, all the ZJ minus CJ values are the greater than or equal to the 0. So we got the optimal solution. So for this we have to move the next step, that is the, we have to go for the second phase. So in the phase 2, consider the final simplex table. So this is the final simplex table with the deleting the artificial variables column of the phase 1. So in the phase 1 final simplex table, we are removing the A1 column, A1 and A2 columns, and it is considering for the solution for phase 2, and we have to carry out the calculation to get the optimal solution. So now we have to modify the table with the removing of the A1 and A2 columns, and moreover we have to modify the cost coefficients. For this one, observe the objective function. Now our objective function is maximize Z equal to the minus x1 minus x2 plus 0s1 plus 0s2. We are not considering the any artificial variables because these artificial variables are removed in the basis. So CJ values are the cost coefficient values, that is minus 1 for the x1, minus 1 for the x2, 0 for the s1, 0 for the s2. So and we have to modify this table similarly here also. So 0 with the minus 1 and minus 1. These minus 1 are the cost coefficients for the x1 and x2 variables. So now once again similarly have to determine the, so ZJ minus CJ values to get a optimal solution. So here Zj minus Cj values I have to calculate. So for first one is the Z1 minus C1, that is the minus 1 into 1 plus minus 1 into 0 minus of minus 1, it is the 0. Next one is the minus 1 into 0 plus minus 1 into 1 minus of minus 1, it is also 0. Z3 minus C3 minus 1 into minus 7 by 13 plus minus 1 into 1 by 13 minus of 0, it is the 6 by 13. And next one is the minus 1 into 1 by 13 plus minus 1 into minus 20 by 13 minus of 0, it is the 19 by 13. So here Zj minus Cj values are the 0, 0, 6 by 13 and 19 by 13. So all the Zj minus Cj values are the greater than or equal to the 0. Then present solution is the optimal basic feasible solution. So for this, x1 value is the basis values, that is the 21 by 13, and x2 value is the 10 by 13. Then you have to substitute x1 and x2 values in the objective function, that is the maximize z star equal to the minus x1 minus x2, that is the minus 21 by 13 minus 10 by 13, it is the minus 31 by 13. But original objective function is minimize z equal to x1 plus x2. So have to multiply with the minus 1. Then we will get the original objective function is minimize z equal to x1 plus x2. So then optimal solution will become the 21 by 13 plus 10 by 13. It is the 31 by 13. So this is the basic feasible solution. So thank you.